Hi class, welcome to our lab on looking at model level assumptions and moving us into a new regression called hierarchical regression. I have a couple helpers here today. Let me see if I can get Sammy to get where you can see him. Come here, Sammy. Come on. Up. He doesn't like jumping up because I don't like him jumping up. Can you see? Can you say hi? Yeah, maybe? He's grouchy because he's old. Yeah, you are getting old. And this is Curly. So they are helping me today and keeping me out of trouble. So we're going to get started. What you'll need is your Lab5 script and the data set called Survey DAT. So I'm going to get to Lab5. And we have multiple regression, assumptions, and we have our hierarchical regression in here as well. So we're going to start by reviewing multiple regression, and it's so that we can just restart that since we've been using categorical predictors for a while. We're going back to continuous predictors, and also using this to jump us into looking at model level assumptions. And we're going to evaluate assumptions related to regression, including multicollinearity, singularity and outliers, and the normality, linearity, and homoscedasticity of residuals. We'll go into more of that shortly. After we get that kind of nailed down, we're going to conduct a hierarchical regression to look at incremental variance explained when we're looking at two levels of a model, or two steps in a model, and report increases in our squared explained in our fx size, interpret results, and look at what we need for writing up. Some packages you're going to be using for this one, as always, tidyverse. And to get our fx sizes for the regression coefficients as far as the standardized beta, we'll need the LM beta. To get our confidence interval for R squared, we'll need MBES. And then these, the core is to get correlation test, like a correlation table. It's nice to get that. But the Broom one, that is where we get our regression diagnostics from. So we'll need that one. So you'll want to install all of those packages, and you can either load them at the beginning or you can load them as we need them. We're going to be importing the data set called Survey DAT. It's the same Palant survey, but in a tab delimited form. So once you've downloaded it and put it where you can access it, you would just import. I put mine in a data folder. And as usual, it retrieves thinking that it's comma delimited, so I have to change that to tab delimited. And then it stretches those variables out properly. And we're not using the categorical variables, so you don't have to worry about changing those into factors. I would change the ID to character, just in case we need to use it. And that looks ready to go. So I have 439 observations of 134 variables here. Yep. So I'm not walking us through preliminary analysis as far as describing the data set and the variables of interest and doing univariate assumption checking. We've already done this a couple of times, and if you need to see it for continuous predictors again, go back to our multiple regression lab video and walk through that. But I want to save more of our time in the video for looking at our model level assumptions and running the hierarchical regression. So we're going to start with this review of multiple regression. If we were to say, how well do two predictors, total mastery and perceived control, predict perceived stress? So our variables of interest would be total perceived stress, total perceived mastery, and total perceived control. So first we're going to tell R that we want a linear model. Again, I'm skipping preliminary totally, I'm just going straight to model. And we're setting up a linear model saying, I'm going to call it MR1, multiple regression 1, the linear model of total perceived stress predicted by total mastery and total perceived control using the data called survey. Now that gets us started as far as with our model is right there, but I know I'm going to want the standardized regression weights, so I need to run the beta. And so I'll go ahead and get a summary that has all of that in it instead of running the summary and then running another one. So I have, here's our unstandardized estimates in this column, my standardized betas, and the significance value. So both predictors are significant. There's my F line for the model, my effect size of the model in R squared, and all of my regression coefficients. So I would need MBES to get the confidence interval for R squared, and that would run from 0.39 to 0.53. And that's what we'll see in the write-up as well. And the write-up is in the lab sheet for SPSS. It's just the same, more or less. There might be a few little differences, like some kind of rounding difference or something between RStudio and SPSS, but they're pretty much the same. Okay, and that we've done before, right? We've done all of the multiple regression before. So this is where I want to start us with assumption checking for model level assumptions. So assumptions based on regression. And those are going to be typically about the residuals. But we'll start with multicollinearity. Multicollinearity is just saying, are the predictors highly correlated? And highly would be above 0.9. So for this, you would run a correlation test between your predictors and just find out what is the correlation. Our correlation between total mastery and total perceived control is 0.5206442, which is nowhere near 0.9. So we're not worried about multicollinearity. For singularity, that's basically saying we need to know that we're only representing an item once in the regression instead of multiple times. And you would see this by looking at the items. There were 7 items that go into the mastery scale in that survey data set from Palat. If I had the items in the regression equation with the total scale, that means the items would be there individually and they're under the total scale. They would be not singular. They would be represented more than once, and that's a problem for singularity. You could also have that problem if the items in the mastery scale were also in the perceived control scale. So if I had items that went into 2 different scales and both of those scales were in the equation, it means some items were not we're being represented more than once, and that would be a violation of singularity. So we don't really test for this. We just got to pay attention to what we're putting in the linear model, and it's fine. But it is an assumption of regression there. Now, to look at some of these others, we're going to need regression diagnostics. There's a word for us. So we use the Broom package to get the functions for requesting regression diagnostics of this model, of this regression model. And the function we're using is called the augment function. So I'm giving a new name to an item that's going to be in the environment. I'll call it mr1.regression diagnostics, just so that I can look at the items in my environment and know what they are. For example, I know this one's the model. I know this one is when I added the beta, the standardized regression coefficients to the model. And I know this one's the data set, the first data set. Like if I had subsetted, you've seen where I'll do like survey.1 and survey.2 and survey.3. So I try to give names in the environment that help me keep track of what I'm doing as well. And that's why I call this that we're making the regression MR1 with the regression diagnostics for it. And you can name it anything you want. Assigned by the function augment being applied to the regression MR1. And then, there it is. And then I will get the summary of that item. So now I have TP stress, TP mast, and TP cois. Those we're used to. But now all these other weird ones, dot fitted, dot resid, dot hat, dot sigma, dot cooksd, dot standard, dot residual. So let's take a look at it a little bit prettier just to get a look. Do the view. And now we can see all of these across. So here, when we're talking about residuals, what is that? The residual is the difference between what the actual data were and what we predicted it to be. For example, on this top one, TP stress, that's the outcome, was 29. But what we predicted it to be with the equation was 28.26128. So there's a difference there. I'm going to grab a calculator here. And let's see what we got going on. The actual data was 29 for that case. If I subtract what the predicted should have been, minus 28.26128, we get 0.73872 right there. The residual is the difference between what was actual and what we predicted it to be. Because remember, that regression equation is predicting, based on the predictors, what the outcome would likely be. And any difference between what was predicted and what it really was is error, the residual, what was left over. Okay. Let's take a look. So we have some things in that case, in that regression diagnostics, right? We have the dot fitted, that's the unstandardized predicted value. This is the one called PRE_1 in SPSS, or _2, underscore however many times you've run it. The resid in this regression diagnostics right here is the unstandardized residuals. This is called RES1 in SPSS. And then the cooksd is the Cook's distance, which tells us if a specific case might be a residual or having undue influence on the regression, might be an outlier. And that's what in SPSS that was called COO underscore. Okay, so let's check out these outliers. It's recommended in Palat that any Cook's distance greater than 1 could be a potential problem. So we can, going over to our regression diagnostics, just sort the Cook's D. That's to the -9. Let's sort it the other way. There we go, 0.095559074. That's the largest Cook's D. And it's not really near 1 at all. It's closest to 0.1. So I'm not seeing a problem with outliers here. So check out your Cook's D and see what you think there. Next is normality of residuals. Now, what is that? It's saying that those errors, those extra left over, if you took them all and laid them out, they should be normally distributed. And whenever we're looking at the normal distribution of something, we can get a visual inspection of it with the histogram. Just like we did with univariate assumption checking, where we would look at normal distribution of a variable by looking at its histogram, we can do the same thing here, because we do have a variable that is the residuals. All we got to do is ask R for the histogram of it using ggplot. And there we go. There's our histogram of the unstandardized residuals. Doesn't look too bad to me. Let's see what Shapiro's-Wilks test says about it. Okay, it is significant. So because it's a significant normality test, it means it violates normal distribution. So I don't know, maybe it's picking up on the spikiness, or it is kind of sharp, right? But you would report that. You would report what you see visually, and then also the test of that assumption. So moving on, linearity of residuals. So the residuals should not be related to the predicted value. We would want any predictors already accounted for in the equation. The error term should be just what's left over, not related to anything. And the way we check out if something has a linear relationship is with a correlation and looking at the scatter plot. So again, similar to when you check out bivariate linearity in that univariate assumption check at the beginning, here we're going to say, is there a linear relationship between the residuals and the predicted values? We can look at the scatter plot of them and just seeing, do we have a positive or negative trend here between the predicted and the residuals? And we can also run a test, a correlation test, to see if there's a significant linear relationship. It looks like, nope, there is not a significant linear relationship there, because it's to the -16th power. That's 15 zeros after the decimal point before you get to a number that's not 0 there. So we see that not seeing any trend, not seeing a correlation between the predicted and the residuals. So it looks like we have no problem with linearity of residuals. Now the homoscedasticity of residuals is saying, is the spread for each predicted value, is the spread of the residuals similar. And what you do is look at this line at the 0, just imagining that line. I think there is a way to add a reference line here. I just haven't done it. And for each predicted value, does it look like you have similar spread above and below that reference line? And that would, if you have unequal, like a lot of spread below the line, but only a little bit of spread above the line, then you have a homoscedasticity violation. And there is, we don't have a test for this that I'm going to have you do. Here you just look at the spread of the residuals and see if you're seeing a difference in the spread there. And there is a way to just get a bunch of regression plots here. What you can do is this one called plot. It's from base R. And it sets up here in the console where you have to hit return to see each plot. It gives 4 regression diagnostics plots, and we only use a few of them. But I'm getting down into the console and hitting enter. So here's the first plot, the fitted values on the x-axis, so predicted, and the residuals on the y-axis. And here, that dotted line is the reference line at 0. And then the red line is the estimated correlation between those two. So it kind of gives you the linearity and the opportunity to look at homoscedasticity in this same graph. So that's nice. The next plot, I'm going to hit enter, is the normal QQ. Now this is similar to the normal PP plot that you would have seen in SPSS. And the dotted line is the expected residual, where the expected prediction would have put everything, like if there was no residuals. But here is where the residuals are coming off of the predicted line. So you could say there's some pulling off of the predicted line at the top and at the bottom. Notice that it's identified a few cases it feels that are out there, possible outliers, but we already looked at Cook's D. So you could say that the normal QQ plot identified 3 potential outliers, but evaluating Cook's D, none of the Cook's D estimates were close to 1. Okay, and then another plot, hit enter. So this one's similar to the first one where we have the predicted values, and here we have the square root of the standardized residuals. It's another way of looking at it, but it's kind of same as the first plot in this series. And then the last plot, we don't use this one, residuals versus leverage. That would be later on. I think Palant does talk about leverage statistics, and it is something you can get out of SPSS as well. But I think we have enough assumptions to look over with these. We have multicollinearity, outliers, and then the normality, linearity, and heteroscedasticity of the residuals. Okay, and then you have all you need for the written, doing the write-up. Let's take a look at that again. Going down to the full write-up right here. So this would be after the preliminary, like preliminary where you describe the data and the variables of interest. You give your reader an idea of what's going on, and you do your univariate assumption check of the normality of your variables, or the homogeneity of variance if you're talking categorical variables. All of that would be in your preliminary. Then when you're talking about your multiple regression, this is where you let the reader know about the regression assumptions, so the model level assumption check right here. And then at the end, you tell your reader about the actual regression. Okay. So then what we're going to go into is hierarchical regression. This is a new or a more complicated regression than you've run before. It's kind of taking multiple regression and adding more information there. And what's going on is sometimes there's variables that you want to control for before you look at your model that you're really interested in. It's similar in concept, but not exactly to when we're talking about the design of a study. When you're designing an experimental study, you want to control for extraneous variables, right? Alternative explanations. And one way you do that control is by random assignment to conditions. And that's so that those individual differences like age or gender or any of these things that you don't have a whole lot of control over are equally distributed in each of your conditions, right? And that's putting controls to secure the internal validity of that study. But sometimes, especially in applied research in organizations or where you don't have the ability to set up randomly assigned conditions, you still want to have some kind of way of knowing, do my variables actually have an effect apart from the things I can't control? So this is a way to statistically control for some variables. And that's what this control is about. It's not random assignment, it's statistical control of possible effects due to confounding variables. Like I can't control age, I can't control someone's socially desirable responding behaviors. So I want to account for the variation that might be due to those confounding variables before I look at the model that I'm truly interested in, which is total mastery and total perceived control, predicting total stress. And we do that by running pretty much two models, a reduced model and a full model. Our first model is going to be the reduced one with just age and social desirability in it. And then the second full model includes age and social desirability, but now also includes the variables of interest, total mastery, and perceived control. So I'll call the first one Model 1. And it's the linear model of total perceived stress predicted by age and social desirability from the dataset survey. And we'll take a look at that. There's our F-test for Model 1, just with age and social desirability, and how much variation in total stress was being explained with just age and social desirability. So 5.7% of total stress explained by that model. And I can get the betas for it, and that's something I would need to make my regression table for step 1 for Model 1. But then I'm moving on to Model 2. And Model 2 is the full model, the one with all of the variables, age, social desirability, total mastery, and total perceived control. That one I'll call Model 2. And I'll have my F line for Model 2, and that's the full model. That's the one I'm more interested in. I'll need my betas, my unstandardized regression weights, and my standardized regression weights. And you see here on my full model, total mastery and perceived control are still significant predictors with the significance right here. And I have my effect size of the model, all the information I need for writing up the full model. So what am I still missing? Well, what I'm missing is knowing the change in R squared. Like, we know that the smaller model, the reduced one, had a R squared of 0.5728, right? And we know the new one, the one with everyone in it, had a effect size R squared of 0.470. So really all I need to do is subtract them to find out what the change in R squared was. And a calculator does the job there. You can just subtract one from the other. But if you'd like to play around with some coding to get RStudio, or to get RStudio to put those values in the environment for you, it could look something like this. I can make a new item in the environment, a new object that is assigned by take the summary of mod 1, so that's the regression information, and pull out of it the R squared value. We never looked at that in specific, but there is one in there called R squared. So run that. So there's the R square value, the 0.57, right, from the first model. And then I'll do the same thing for model 2. I want the R squared out of it, assigned as a value in my environment. And now I can just have R act like a big old calculator, and I'll give a new name to a new object in the environment, and I'm just saying take the one minus the other. And that would be the change in R squared between model 1 R squared and model 2 R squared. And that's my delta R squared. But now we're ready to do those model level assumption checks for the hierarchical model. And we're looking at the final model. We're not doing assumption checks on every step. We're only doing our model assumption checks on the final model, the big one, of the hierarchical regression. So similar to what we ran when I was just introducing you to the concepts, we want to check out each element. Multicollinearity, that is done by looking at the relationships, the linear relationships in these variables. Specifically, we're interested in the predictors. If the predictors are too highly related, there's a problem with multicollinearity. So I'm going to pull from a prior lab. This would have been more in our first data handling labs, where we can get a correlation table by getting a smaller subset of the data set so that we don't have so many 134 variables there. So I'm going to request a subset, and then I will use the correlate function in the package core to make me a little correlation table down here. Cool. And I'm interested in these two predictors. What is the relationship between them? Total perceived control with total mastery. It's coming in at 0.521, nowhere near 0.9. So I'm not worried about multicollinearity for this model. Another thing we need to check for, it will need the diagnostics, right? I'll need to use that augment function to get the regression diagnostics for this model. So I'll call this one model 2 regression diagnostics using the augment function on model 2. And I'll take a look at that. Again, I have my outcome, and I have what the predicted value was, and what the difference is the residual. Cool. With that, now I can check out these other items like outliers, normality, linearity, and homoscedasticity of the residuals. For outliers, we want to check out the Cook's D. So I'll go over to my regression diagnostics and sort the Cook's D. That's the little, and now these are the big. This is descending. And the way I can tell is because if I sort it the other way, I have that to the negative 0.9 power, which is that 0.0000000. So that's ascending from lowest to highest. So I'm just going to hit it again to get descending. And the largest Cook's D is 0.058, nowhere near 1, which is my cutoff. So I'm not worried about outliers here. How about the assumption of normality of residuals? Again, when I'm checking normality and I want to take a look at it, all I need is a histogram. And I already have the residual as a variable in that diagnostics that I asked for. So I'm going to use ggplot to ask for a histogram of the residuals for model 2. There's that one. I can check out Shapiro's test, and this one is also significant, so I would report that I have a significant Shapiro's-Wilks test, and visually I think it looks pretty normal, but that's fine. Very subjective, the visual inspection of the plots here. Next, linearity of residuals. Are the residuals linear related to the predicted values? We hope not, but let's check it out. We'll look at a scatter plot between the residuals and the predicted values, and we'll do a correlation. So definitely the correlation is not anywhere near worrisome there. -8. So it says it's seeing a negative correlation, but to the negative 16th power means 0, 0, 0, 0, 0, lots of zeros before we get to that 8. So it's pretty much 0. Alrighty, and the last, homoscedasticity of the residuals. Here, we're visualizing that 0 reference line across the middle of that scatter plot and saying, are the residuals kind of equally spread over and above each point? Like, take 25. Do I have about the same amount of residuals over as under? And again, those diagnostic plots, if we want to see them all just kind of together, we got fitted to residuals with the line there, both the dotted line, which is the reference 0 line, and the red line is the estimated correlation between those two. And I'll hit return again for the next plot, the normal QQ, and seeing that they go off the estimated line there, what my regression estimated it should be and what the values actually were. That's the residuals, the difference between them. I'll hit return again. There's a similar fitted to residuals graph. And then the last one is about leverage, which we don't use that one. Okay, now we have the information we need for the regression table. And the regression table itself, hold on, get down, it's the last, almost the last page. page 9. So I have in step 1, what was my R squared, what were the regression coefficients and the betas for them. In step 2, I have is all of the predictors in that one. So I have the R squared, but also the change in R squared, and that only total mastery and perceived control remained as significant predictors there. And then I grabbed a couple of plots just to be able to have something to refer my reader to help explain what I'm seeing. And that is it. So that is it for our model level assumptions and hierarchical regression in R. And I will see you in class.